Hi, everyone. We are project 6, and our topic is a cellbook type trace formula for GL3FQ. The abstract is that we present our work on extending the cellbook type trace formula to higher dimensional finite groups of Lie types. My name is Jiyuan Lu, or Maki. I will talk about the trace formula and original cellbook trace formula. So first of all, let's recall from the midterm presentation that a trace formula is an equation of the following form. The one side is the sum of some spectral terms, and the other side is the sum of some geometric terms. We have the theorem which says that if A is an n by n complex matrix, then the sum of all the eigenvalues is equal to the sum of the entries on the main diagonal. We have the Poisson summation formula, which says for the finite abelian group, for the abelian case, if G is finite abelian group, gamma is a subgroup of G, and then for any f, a function from G to C, we have that 1 over the size of gamma times the summation over gamma in gamma f of gamma is equal to 1 over the size of G times the summation over all chi in G mod gamma hat f hat of chi, where G mod gamma hat is all the inequivalent irreducible unitary representations of G such that chi of x is equal to 1 for all x in gamma, and f hat is the discrete Fourier transform of f. We have a similar formula for the non-abelian case, but it's a little bit more complicated. So for any finite group G, it can be non-abelian, and the gamma is a subgroup of G. Therefore, any map f from G to C, we have that the sum over pi in G hat, trace of f hat of pi times m of pi rho is equal to summation over x in gamma mod G, the summation G in gamma f of x inverse Gx, where this rho is induced representation of the trivial representation. And f hat of pi is defined to be summation over G in G, f of G times pi of G inverse. And here, pi in G hat means pi runs through all the inequivalent, irreducible unitary representations. And we will later use an analog of this pre-trace formula in our research, and we'll talk about that later. And then let's also recall from the midterm presentation that a Poincare upper half plane is a very important geometric object that we are interested in. So Poincare upper half plane is H. It consists of all the complex numbers where the imaginary part is greater than 0. And we have the metric tensor on H by dx squared is defined to be dx squared plus dy squared divided by y squared. And we have the original point of H defined to be I, and that the PSL2 of R acts on H transitively and isometrically by Mobius transformation or fractional linear transformation, which if gamma is ABCD, tau is in H, then gamma of tau is defined to be A tau plus D over C tau plus D. This is indeed a group action. And also it acts transitively and isometrically. Here, isometric just means it's isometric under this metric tensor. And then we have that the stabilizer of I, the original point is SO of 2, the special orthogonal group. Then we can identify this Poincare upper half plane H by this PSL2R mod SO2. So later, we'll also talk about the finite Poincare upper half plane, and also we generalize it to 3 dimensions. Okay. So let me simply talk about this original cellbook trace formula, which is which gives the intuition of our research. And so if f is a k-invariant function H with complex support, then we have this formula where on the left-hand side it's a spectral side, and on the right-hand side it's a geometric side. So you can see that the first term, the area of gamma mod H times f of I, it is a central terms. And we have the hyperbolic term, we have the parabolic terms, and also the elliptic terms, but they are a little bit complicated, so I don't write any all of them down. But so we will introduce a similar cellbook trace formula going on, and this cellbook trace formula we can have a similar one, but it's a little bit different because we don't necessarily have it's true for all f which satisfies some condition, but we still have a trace formula for the finite upper half plane of the 2-dimensional case, and also we generalize it to 3-dimensional case. Okay, so let me turn the presentation to the second part, which is presented by Daksh.
Hi, I'm Daksh. I'm going to talk about higher dimensional cellbook trace formulae. So Maki just told us about the original cellbook trace formula on the upper half plane. So it's natural to wonder if there are generalizations of this to higher dimension. And indeed, there has been a lot of work and interest on this problem. And so I won't really go into too many details of these different works, but indicate their different directions and an application to kind of show that this is really a fruitful direction of research. So the first kind of a lot of different papers in 80s and 90s. One of them was Flicker's work on GL3R, in which he generalizes work by Langlands on GL2R. Then there's Wallace's trace formula for SL3Z acting on SL3R mod SO3R. And so this can be seen as the kind of direct analog of the original cellbook trace formula. And the formula that she proves over a series of papers spanning about 10 years, it's quite an explicit trace formula, kind of suitable for number theoretic applications. And it's the kind of formula that we are trying to prove for GL3FQ. And Balaj will talk more about this later on. A third kind of very different approach is Arthur's adelic version, in which works over the ring of ideals, which essentially is you work over all the completions of the rationals, so the reals and the QP-adics. You work over all of them at once, and this sort of gives you control over tricky convergence issues, and which is quite a big concern for these trace formulae. And so an application of these generalizations, so there are quite a few applications of these, and they tend to be quite sophisticated. Here is one by Dietmar and Hoffman. They prove a nice asymptotic for complex cubic extensions for the class numbers. So the partial sums of the class numbers of orders in complex cubic extensions ordered by the regulator, they prove is asymptotic to e to the 3x over 3x as x tends to infinity. And this is really paralleling breakthrough result of Sarnak's, in which he proves a very similar result, e to the 2x over 2x for real quadratic extensions. And the way he achieves this is by using the original Selberg trace formula. He identifies regulators with lengths of closed geodesic, prime geodesics on the modular curve, and uses the prime geodesic theorem, which is a consequence of the Selberg trace formula. And so this was quite a spectacular application of it. And Dietmar and Hoffman use a generalization of the Selberg trace formula to prove this for the complex cubic extensions. Now, C will talk about the finite upper half plane, which is the setting that we have been working on.
Hi everyone, my name is C. I use they, them pronouns. And right now I will take us back to the two-dimensional case and consider an even simpler model of the upper half plane, which is finite, and look at the trace formula there. So this model was originally proposed by Audrey Terrace, and we replaced the field R with a finite field FQ, where Q is a power of a prime. And then we pick some non-square in this field, delta, and we simply take the square root of delta, which would not be in the field, and plop that where I used to go in the complex number case. So then we would have this finite analog of complex numbers, and we call this the finite upper half plane. And as Mackie mentioned before, we could identify the Poincare upper half plane with this group quotient here, PSL2R mod SO2. So similarly, we can do the exact same thing here and have this group quotient where GL2FQ is a group that acts transitively on HQ, on our new upper half plane. And it acts also by Mobius transforms or linear fractional transformations. And similarly, again, we mod this out by K, where K is the stabilizer of square root of delta that we identify as the origin of the space. So on this space, we end up with a new trace formula. And this formula comes mainly from representation theory. So as Mackie introduced before, there was the pre-trace formula. We play around with it. We have the extra condition that HQ is actually a symmetric space. And this allows us to simplify the left-hand side here a little bit. So whereas in the pre-trace formula, we had the Fourier transform of F on this left-hand side, this time, because HQ is symmetric, we can just simply write the spherical transform of F, which is a little bit easier to work with than the Fourier transform. So this trace formula that Audrey Terrace calls the Cellbook trace formula for finite symmetric spaces, it now relates the spherical transform of F and the information about the irreducible representations to, on the right-hand side, information about the different conjugacy classes of G. And so throughout our presentations so far, and even the midterm presentation, we've really emphasized how with a trace formula, you want to have spectral information about an operator and also related to some geometric information. Now, I don't know about you, but this formula here, this symbol soup, does not really look like it has any geometric meaning to it. And if you recall from our midterm presentation, we actually had a different presentation of a trace formula that was for the finite regular graph. And with that, we were able to relate, some of the information about the operator itself with information about the different conjugacy classes of geodesics of the graph. So this just means what types the geodesics are. So here we ask, can we also find a graph that maybe is this formula is relating? So we're actually able to make a graph out of this space, HQ. We take this definition here of a D that we call a distance in quotations because it's in HQ and not an actual number. But the important part about this is that this D is a point paired invariance under the action of G. And so we can build a graph on this based on this definition. Basically, we plop down the points of HQ. These are the vertices. And you connect any two vertices when they are a distance A apart, where we fix A at the beginning. And so these graphs are actually really nice. So first of all, these graphs are Cayley graphs. Cayley graphs are generated by groups. So if we pick the right group, which is like basically HQ itself, and we pick a specific generator, then we can use our group theoretic intuition to help us understand what is going on with these graphs, which in turn will help us understand the trace formula. But the more important thing about these graphs is that they are actually regular graphs. They are Q+1 regular. So this makes us think about the last trace formula that we had for specifically regular graphs. And unfortunately, there is not really an obvious connection between the regular graph trace formula and this new representation theory heavy trace formula. So this is quite a disappointment. But from here, I'll pass it on to Balazs, who will introduce you to some of the things that we have tried to do inspired by this model and the things that we have thought about here, as well as some of the earlier continuous stuff.
Hello, my name is Balazs Németh, and in the final part of our presentation, I will talk about the trace formula for the general linear group of degree 3 over a finite field FQ. As Daksh pointed it out, it's of natural interest to generalize the Cellbook trace formula to higher dimensions, and motivated by the finite example C has introduced to us, over the past few weeks we have been working to generalize the above trace formula for the group GL3FQ. However, a priori it's not clear what the generalization of the finite upper half plane HQ should be, because in the two-dimensional case we had the natural analog of the complex number system and the Poincare upper half plane. However, in 3 dimensions we can't really find such a thing. So instead, we will turn to an algebraic construction, assume that Q is of the form 3t+1, then it's not too difficult to prove that there exists a delta in FQ such that delta is not a cube, i.e. the polynomial x cubed minus delta is irreducible over FQ. Then, if we adjoin a cube root of delta to FQ, then we obtain a degree 3 extension of fields. That is, FQ cube root delta will be a 3-dimensional vector space over FQ with natural basis 1, cube root delta, and delta to the 2/3. The finite upper half space will be defined as the set of pair of points alpha beta, both from FQ cube root delta, such that alpha, beta, and 1 are linearly independent over FQ. Note that this is actually similar to the two-dimensional definition. There we require the imaginary part to be non-zero, but that's equivalent to x plus y root delta and 1 being linearly independent over FQ. Now G acts on HQ via fractional linear transformations, much like GL2FQ acted on the finite upper half plane via Möbius transformations. It's not too clear why this should define an action. This is really an action on a subset of the projective space P over this vector space. A projective space is defined over any vector space. What we do basically is we exclude the origin and then identify each vector with its scalar multiples. And since on this vector space G has a natural action via linear transformations, that action will actually carry through to the projective space. Let us investigate this action a bit further. Define the origin to be this point P0, and then we can calculate the stabilizer of P0 under the action of G. We call this subgroup K, and this will be a rather nice subgroup of G, isomorphic to the multiplicative group of the field FQ cube root delta, much like in the two-dimensional case. This will be our finite analog of the rotation group SO3. If we define the affine group of G as this way, where the last row should be 0, 0, 1, then this affine group actually acts transitively on HQ, which implies that G itself will act transitively on the finite upper half space. This means that, just like in the two-dimensional case, we can identify HQ as the quotient space G mod K, and we can call HQ a homogeneous space, and every point in HQ can be identified with a left coset GK in G mod K. We can apply the usual pre-trace formula to this setting. We take G to be GL3FQ, gamma to be a subgroup GL3FP, rho to be the induced representation from gamma to G, and F a function from G to C, which is K by invariant, and this pre-trace formula is valid. This relates orbital sums of F over conjugacy classes of gamma to irreducible representations of G appearing in rho in the spirit of a trace formula. So over the past few weeks, we have been working on writing down orbital sums and characters to produce an explicit version of the trace formula for this setting. To our knowledge, this is an entirely new piece of mathematics. We haven't found any papers dealing with trace formulae for finite upper half spaces of higher dimensions in literature. But the natural question would be, is there a geometric connection? Because most of our formulae were group theoretic, representation theoretic, algebraic, and we wish to find a geometric connection. Unfortunately, there is no natural distance on HQ as there was in the finite upper half plane case, but we can find a 3-point function D mapping triples of points on HQ to the field FQ that is invariant under the action of G. And just like in the two-dimensional case, we can construct now hypergraphs on HQ using this invariant, and these hypergraphs will be parameterized by the elements of the field FQ. Now, a hypergraph is a generalization of a graph where each edge may connect more than 2 points, and the free uniform hypergraph is a graph where every edge connects exactly 3 points. We will try and investigate how these hypergraphs relate to the above trace formula. What does the trace formula say about, for example, the adjacency operators of these hypergraphs and their spectra? And in general, it would be interesting to investigate the general GLNFQ case. The above construction of the finite upper half space can be generalized, and it would be nice to see some aspects of trace formulae for those sets. Thank you for your attention, and feel free to ask any questions.